In this video, we are going to consider just one situation. Imagine you have a mass falling to Earth, and the only forces acting on your mass are downwards due to the force of gravity and upwards due to air resistance. For example, we can imagine a skydiver of mass in kilograms who's jumped out of an airplane and they're now falling to Earth. From Newton's second law of motion, we know that the total force acting on the mass is equal to their mass times acceleration. That's how we come up with this first order differential equation. So on the left, we have mass times acceleration. On the right, we have the total force acting on the object. Let me diagram what's happening here. So we have a mass. I'm not going to try to draw a skydiver. Okay, maybe I will. So here's our skydiver. Okay, they're falling to Earth. Let's set this to be the positive sense of direction. So this is the direction of motion. They are falling downward, so their velocity going down is traveling in the positive direction. So gravity is working in the direction of motion. So we have mass times gravity. That's the force acting on the skydiver downwards due to gravity. However, notice that we are subtracting b, where b is just some positive coefficient of air resistance, times the velocity itself. So let's talk through two things. Why is it b times v, and why is it negative? As the skydiver is falling, the air resistance is essentially pushing up against them. It's kind of like if you move your hand in water. You think of the resistance of the water on your hand as analogous to air resistance. You have the water pushing against your hand. So this sign here is negative because it's acting against the motion. It's pushing us upwards. And then b times v is really communicating to us that the force on the skydiver due to air resistance is proportional to the velocity itself. So b you could think of as a constant of proportionality here. Now what that's saying is the faster the velocity, the greater the air resistance, whereas with no velocity, the air resistance is nothing. Again, if you compare like water, I just think water is easier to feel resistance in compared to air. Like I don't feel that much resistance when I move my hands around. If your hand is just sitting in water, you don't really feel any water resistance against your hand, right? Because it's just sitting there. If you slowly move your hand in water, you feel some resistance. Now, if you try to really rapidly move in water, say you're trying to run in a swimming pool, you really feel the resistance against your motion. And that's the same thing that's happening here with our falling mass. The faster you fall, the greater the air resistance works against you in the upwards direction. Okay, so this first order differential equation is straight from Newton's second law. We have mass times acceleration is equal to the force acting on this object. Let's answer a little question about that positive coefficient of air resistance, and then we'll go into analyzing our differential equation. Ultimately, what we want to answer is what happens to the skydiver over time? Now, realistically, they fall to Earth. Okay, but numerically, what's going to happen to the velocity if we can allow time to go to infinity? Okay, so for our first question, here I just want to do a little exercise in dimensional analysis. This differential equation should be dimensionally consistent, meaning that all of the terms have the same SI unit. So let's figure out what the unit for B should be. On the left, we have mass times acceleration. So mass was in kilograms. So what's going on the left-hand side? Mass was in kilograms. Acceleration is meters per second squared. Why is it second squared? Because it's the rate of change of velocity with respect to time. So that's meters per second per second. On the right-hand side, we have mass times gravity. It's very similar to this one. We have mass times gravity. The force downwards due to gravity is like an acceleration, so it's meters per second squared. You're accelerating downwards due to gravity. So here's the first unit. Okay, those two match. That's good. And then what we're missing is the unit for B times velocity itself. So that's meters per second. What we would like for this product to be is kilogram meter per second squared. So we have a meter, we have a second, so we need kilograms per second. So that is the SI unit for that coefficient due to air resistance. Okay, so let's go back to our differential equation now. What we're going to do is first generate a picture of the slope field. So we will just graph a little picture of line segments in the TV plane that give us a qualitative feel for how solutions to this differential equation would behave. So if you know your velocity, can you kind of read off of the graph what would happen to the velocity over time. That gives us a picture for what happens. And then we will take this differential equation, recognize it as separable, separate the variables, and actually come up with an explicit solution for the velocity over time. Let's start our analysis of this differential equation by creating a slope field for it. This will give us a nice idea of the qualitative behavior for any solution to this differential equation. So what I'm going to do is divide out by the mass. The mass is greater than 0, so that's a safe thing to do. Our differential equation put in that form looks like dv dt, the rate of change of velocity with respect to time, equals g minus b over m times v. If you're wondering why it wasn't written in this form to begin with, it was because of we wanted to see the Newton's second law kind of presented in the starting form of this equation. But now in this form, we can say, hey, this is an autonomous differential equation. There's no time dependence here. We have v, but we don't have t. So what we can do in order to create this slip field is we can pick different values of the velocity. And then once we take the velocity and we have an idea of what dv dt is for that particular velocity, we just stretch that slope to the right because it's an autonomous differential equation. What's also nice about this differential equation is not only is it autonomous, but it has a nice straight line relationship between v and v prime. So in order to graph this slope field pretty quickly, what I'm going to do is create a picture of how v and dv dt relate to each other. So let me put dv dt here on the vertical axis and v on the horizontal axis. This is a straight line equation. So we have slope negative b over m. B and m are both positive, so this is going to go down. We have a y-intercept, or really a dv dt intercept of g. Okay, so we're going to go down from that. Let's see, what is the v-intercept? If you set the left-hand side equal to 0, you get bv over m equals g mg over b. Okay. So this is mg over b. Okay. So we have a straight line connecting these 2 points. This gives us a way to relate. This is it was supposed to be a straight line. Got a little worried about it as I started to sketch it. Okay, this is the line determined by this equation. This gives us a way to pick a v and then figure out what dv dt is based on that choice of v. Then we'll put that on our slope field. Okay, let's figure out what mg over b is. Okay, well, if the velocity is mg divided by b, that means that dv dt is 0. If you plug in mg over b here, you get 0 on the right-hand side. And then that's true regardless of time. So for all time, if the velocity is mg over b, the rate of change of velocity with respect to time is 0. So this is an equilibrium solution. If the velocity is that number, mg over b, it's going to stay there forever. We don't have m or b specified in this equation. I'm working kind of a generality, so I'm just going to say there is mg over b on the y or the vertical axis. Since this is an equilibrium solution, what we're going to do now is just graph a bunch of little line segments straight across to the right, which are flat, indicating that if your velocity is at that level, mg over b, it's going to stay there forever. Now, if we want to look at velocities above or below that level, we can see how the rate of change of velocity with respect to time would change. So if we come below the equilibrium solution, then v prime is positive. And then the farther below we are, so if I move farther and farther to the left, the dv dt values go up and up. So qualitatively, we can compare being just underneath the equilibrium solution to being quite underneath, if you will. So I'm just going to add some slopes here just under the equilibrium solution. They're going to be positive, but not too steep. And then as we fill in downwards, the steepness is going to increase to indicate that the acceleration increases as your velocity shrinks to 0. This y-intercept up here, by the way, is g, and that should make sense because if the velocity is 0, say you're a skydiver and you've just jumped out of the airplane, maybe you're essentially falling from rest. then if you are instantaneously having zero velocity, then air resistance can't work against you because you're like instantaneously your velocity is zero. So the only force acting on you is downwards due to gravity. So that's why this intercept up here is g. Same story for going the other direction. So if our velocity is over the equilibrium solution, then our acceleration is slightly negative. So let me add some of those slopes. And then the faster we go, the greater our velocity, the more we decelerate, if you will. So the acceleration is negative and it's getting steeper and steeper as we go up over the equilibrium solution. Okay, so this is our slope field for this first order differential equation. And it's giving us the qualitative idea for solutions to this differential equation. All solutions over time should tend to this value mg over b. So whether your velocity is low, maybe you're falling from rest, you're going to speed up, your velocity will increase, and then over time, it should approach this number. Now, realistically, you might open your parachute or you might hit Earth or something like that, but just imagine you could fall forever. Over time, you would be approaching this number. On the other hand, like if you were shot out of a cannon really fast or something so that your velocity was really, really fast, you would actually slow down, you would decelerate. So air resistance would work against your motion so much that your speed would slow down as you fell to Earth, and eventually over time you would be approaching the same velocity. In fact, we call this the terminal velocity for this differential equation. Terminal velocity meaning that everybody goes to that velocity as time goes to infinity. All autonomous first-order differential equations are separable. So let's use separation of variables to get the solution for the velocity over time. What I'm going to do is just divide the right-hand side over so that we have the mass from the left-hand side divided by the mass times gravity minus b times the velocity, dv equals just 1 dt. Okay. You could go ahead and anti-differentiate the left-hand side if you want to. I'm going to use a u substitution. It just helps me see it a little bit better. Let me set u equal to the denominator, mg mg minus bv, so that du is negative b dv. So that about negative m over b. I wrote vd. That's very strange. I meant to write dv. Negative b dv. I was like thinking about the division or something. Okay, so that we have negative m over b du is going to replace m dv. All right. I may have made it worse instead of better, but this is the u substitution that I'm going to set up so that for the left-hand side, 1 over mg minus bv is now 1 over u, and then m dv is going to be negative m over b du. That's just a constant. Let me go ahead and anti-differentiate the right-hand side with respect to t. That's just going to be t plus the first constant that I'm going to identify in this computation. Let me write one more line down here and then we'll carry over. The antiderivative of 1 over u is natural log of the absolute value of u. So this left-hand side is going to be negative m over b natural log of the absolute value of u equals t plus this constant. Okay. I am going to now multiply both sides of the equation by negative b over m. That leaves us with natural log of the absolute value of u on the left and negative b over m t plus c1 is a number, mb, these are all numbers. I'm just going to write c2, where c2 is negative bc1 divided by m. Okay, but this is just a little bit simpler. To isolate u, which we will eventually replace with mg minus bv, we will take both sides and raise e to each side. On the left, we have the absolute value of u. I think I'm ready now to go back to mg minus bv. So on the left here, I'm going to write the absolute value of mg minus bv And then on the right, we have e to the negative bt divided by m times e to the c2, where I'm going to break apart the sum and the exponent here as the product of two exponentials. E to the c2 is yet another number, so I'm just going to write c3. Where again, if you keep track of your constants, c3 is e to the c2. Right. We can get rid of these absolute values. So this is positive. C3 here is positive because it's an exponential. So e to anything is always a positive number. What I'm going to do is drop the absolute values on the left and then write C4, where that could be C3, it could be negative C3, it could be 0. It's going to absorb essentially the sign of mg minus bv. So getting rid of the absolute values, this is going to be mg minus bv equals like an absorbing constant, C4, e to the negative bt over m. We can now isolate v. Now I'm going to do too much at once. So how about negative bv is negative mg plus c4 e to the negative bt over m, divide out by negative b, and we have the velocity is mg over b, might recognize that number, plus c4 divided by negative b. I'm going to write c5. Actually, I'm just going to write c. I think that's our last constant. So how about just c? E to the negative bt over m. Okay, we've done the separation of variables now. I'm going to step away for a second to let you finish this process if you're still writing this down. And then I would like for you on your own to solve for this constant c, using the fact that our initial velocity is something. So in this problem, I didn't want to give you a specific example so that we could work with these quantities in generality. So let's just call the initial velocity v sub 0. To use our initial condition, what we want to do is set t equal to 0 and say that at the moment the falling out of the airplane started, we were traveling with a speed of v sub 0. So that's just some number. And when you do that, e to the 0 becomes 1. So you're left with c equals the initial velocity minus mg over b. I'm going to go ahead and rewrite v now using that. So the velocity over time for this free fall motion is going to be mg over b plus, where I had c, I'm going to replace that with the initial velocity minus mg over b times e to the negative bt over m. So that is an explicit solution for the velocity over time. Let's just check a couple of features that should agree with what we saw with the slope field. So first of all, let's just check that c makes sense. If I plug in t equals 0, this becomes 1. The mg's over b will cancel, leaving us with the initial velocity, so that checks out. What happens as t goes to infinity? As t goes to infinity, this exponent up here is going to go to negative infinity because b and m are positive. We have this leading negative term. T is going to infinity. So this behaves like the left-hand side of the exponential function, meaning that this goes to 0. So this whole part of the solution will vanish, leaving us with just mg over b. And that agrees with what we saw with the slope field. This is that terminal velocity. So over time, regardless of the initial velocity, whether it's very fast or falling from rest, the velocity over time will tend to this terminal velocity. So we can see that from the slope field qualitatively, or here we were able to solve it explicitly.